Last one. We're talking about a piece of A4 paper, which has the dimensions 21 by 30 centimeters. It's possible to create a box by cutting out the corners and folding it up, as you can see in this diagram. We want to develop a cubic model for the volume of the open box that can be created using this method. So volume, when we're talking about a formula-based model, which I don't know if you remember on the whiteboard, it used to be up there. Hopefully it'll be up there by the time you come back in next time we see each other. That we can either create a system of equations by plugging in points, and we have to have 4 points for a cubic equation. We could plug in values to solidify a formula for a very specific situation, 80 air density at sea level. Or we can do a formula-based model. And a formula-based model starts with, hey, we're talking about volume of a box. I know how to find the volume of a box. The volume of a box is length times width times height. Then we say, wait, I only want one input, right? I can only have one input. And here I have 3 inputs. So I need to make sure I can find a way to create other relationships such that I can substitute out these inputs such that the only input remaining is one variable, like our area problem from last unit, that we can't have more than one input. So what we did is we replaced one of our dimensions with another relationship that we found within the problem, right? So our goal is to find relationships involving these dimensions such that we only have one input. So we start with our formula, then we go back to the problem and say, what relationships can I create? Well, there's a few things to notice here. So that's the kind of thinking that we're doing here, is we're noticing, right? Notice that this is x, this dimension, and this is x, boom, which means I'm cutting out squares from the corner, which means that this dimension and this dimension, which fold up to make the box, right, are the same length. And they're both x. And when I fold it up, if I were to fold up that lip on either side, that length that ends up getting glued to the other length is the height here. If that does not make sense, feel free to try and do this on your own. Cut out squares from the corner of a paper and see what happens when you bring the corners up. But the idea is that if I cut out a square and pinch that together to make a box, the height of my box would be this length right here as I fold it up. So that's this. This length that I cut out is x, which is here, and as I fold it up, it becomes, technically this would be that, but you get the idea that that would be x. I don't know if I'm doing a great job of explaining, but hopefully it makes sense. If not, tell me the next time we see each other and we'll work on it. Okay, so I know that that's x. I've got one dimension already. Let's call that height. Whew, okay, so height is now x, but now I have still 3 unknowns, right? L, W, and x. All right. Going back into the problem, other information has been given to us, right? It says that it's a 21 by 30 centimeter piece of paper. So if I go in here and say, okay, well, that is 21 centimeters and that is 30, it would have totally been okay if you flipped those around. Then I know that this will be our new width, right? This dimension right here is the same as this dimension. And I know that this dimension right here would be this dimension. So I need to find a relationship here, hopefully that involves x, in order to be able to make more equations. When I'm saying find a relationship, that means find some way to make another equation or expression. So take a second and write down some ideas about a relationship that you think you can create involving x and those side lengths. Hopefully piecing together that we know that this whole thing is 30, and we take out this, and we take out this in order to get this remaining side length. What we've done is we've taken out an x on this side and an x on this side, which means that whatever this was, 30, it's now 2x less than that. And notice that this guy, we also took away this dimension and this dimension, which are both x's. And so now this becomes 21 minus 2x. So this is 21 minus 2x, and this is 30 minus 2x. So if I go back in here and say length here, which doesn't really matter which one's length, which one's width, and which one's height, but length is going to be 21 minus 2x. And width is 30 minus 2x. And height is x. And now, now I've just created an equation where the only input I have is x. I found a relationship for length that involves x, width that involves x, and height that involves x, such that when I substitute them all out, the only thing that's left is x. So this is your formula-based modeling that you need to create. So when you're starting with a geometry formula, which is more likely what you're starting with, the goal is to then say, what other equations can I make in this situation such that it substitutes out for another variable? So that way I can only have it be of one variable. This is v of x. So now I could write and graph this whole thing and say it's only talking about one dimension, but it's talking about how the volume would shift depending on the boxes that I cut out. If I cut out a larger box, a larger square, I might have a smaller volume in the end. And that's it. There's a ton of space there, but it's because I did a lot of talking up here. But that is it for that space. All right, so now we want to decide a reasonable domain. So as always, we're talking about real world stuff, which means we're not going to be talking about negative numbers. So we know for sure that x must be greater than or equal to 0 because we can't have the squares that we cut out be less than 0. The other thing I want you to realize is this relationship here, that I could make these boxes or these squares that I cut out bigger and bigger and bigger. But at some point, the dimension, the size of the boxes or the squares that I cut out on either side has to stop, because I can't cut out even squares on both sides if the square that I cut out is more than halfway. I can't then cut out that square again because it's not an even square that's being cut out from either side. So we're limited in the fact that at some point we hit halfway. And we just know that x can't be longer than halfway because that's 21, and we would then cross over and it would be too much. We would be taking away too much that we don't have. So that's the other limit on our domain, is that x can't be larger than 15, or that's 10.5, half of 21, 10.5. Well, 10.5 is our limit before 15 is our limit. We'll hit 10.5 as a stopping point before we hit 15 as a stopping point. So that means that we're actually limited at 10.5. So x must be less than, strictly less than 10.5. Because if it was equal to 10.5, then we wouldn't have something to fold up to make it the box. So if I wanted to turn that into a domain, x such that it lives between 0 and 10.5. All right. Find the dimensions of the open box with the largest volume that can be created using this method. Okay, first of all, we're going to graph it, and then we're going to find our maximum, which I think we all feel pretty comfortable with. If you were on a test and you got stuck and you were like, I cannot figure out how to create this model, our thought is that, oh, it's already there. Our thought is that we should make something up, right? If you make it up, then you can at least get these follow through points here. So on a test, remember that, like, if you don't know how to find it, if you spend way too much time trying to find the equation, make something up such that it would have a maximum somewhere. Make sure with parentheses in graphing, it's like one kind of weird tidbit about your graphing calculator is that you put a multiplication between the parentheses. Only when graphing on your calculator is that, like, important. Okay. So we graph it and it looks really weird. We always start with standard and then we go to fit and see what happens. It doesn't always turn out quite as nicely as that. We might need to still zoom out or we might still need to do something else. But we've got a pretty nice looking graph right here. So don't forget to do zoom fit. Okay, we want to find the maximum point. So I'm going to find the maximum. And the maximum is 4.061140. It's in scientific notation. I just moved the decimal 3 times. And that's that. So that's the vertex, which is great because I see largest, in other words, maximum, and I'm like, oh, okay, that's going to be the vertex. Make sure that you're reading the instructions. It says, what are the dimensions of the box that would have the largest volume? So we found the largest volume and the value of x, but those are not the dimensions of the box. That's just the height of the box. That's one dimension. So we need to make sure that we have length times width times height. So our height would be 4.06. Remember that our length was 21 minus 2x. So go ahead and find length on your own. If we do 21 minus 2x, 2x is like 8.12. 21 minus 8.12 ends up being 12.88. Go ahead and find the width. Remember that the width was 30 minus 2x. Ba-boom. So that ends up being 21.88. And that would be your answer. Those are the dimensions that would get us to the largest volume. So make sure that you're reading what the instructions are and what it's asking you to do, and don't just give the x value. You need to make sure that you're giving the full dimensions. It then says to calculate the volume, which is really just a multiplication of those three. You also got that volume up here. So if you multiply these 3 dimensions together, you get 1,144.7. But if you wrote it as 3 significant figures, you would get this number, which is the same as what your calculator gave you. So just remember that your calculator always does 3 sig figs as well. All right, that's all I have to say. Good job.